Imagine waking up tomorrow and suddenly Google is gone, YouTube won't open, Netflix disappears, even your bank's website is impossible to find. The internet is still running, so what just broke? The answer is something almost nobody thinks about until it stops working. Every single website you visit has a numerical address, but your brain remembers names, not numbers. Imagine memorizing the IP address of every website you use every day. Nobody wants to do that. That's why DNS exists. Think of it as the internet's phone book, but much smarter. But what actually happens the instant you press enter? Your computer immediately starts asking questions. Where can I find YouTube.com? First, your browser checks whether it already knows the answer. If it's not there, then your operating system checks its own DNS cache. Still nothing. Meet the Recursive Resolver. Its job is simple. First, it checks whether it already knows the answer. No luck. Now the real journey begins. First stop, the root server doesn't know the website, but it knows who might. Next stop, the top-level domain server. It doesn't know the IP either, but it knows exactly where to find it. And this is the server that knows the real answer. The answer begins its journey back. Now your computer finally knows where the website lives. But here's the twist. Finding the IP address is only the beginning. Your browser still has to build a connection to the website, and that's where the next part gets really interesting. But DNS didn't download the website. It simply helped your computer discover where to find it. Think of DNS as the address finder. Once you have the address, other networking protocols handle the actual connection. And here's the clever part. Your computer doesn't necessarily repeat that entire DNS journey every time. DNS information can be cached by your browser, your operating system, and the Recursive Resolver. That cached information isn't permanent. DNS records have a TTL, time to live, which tells caches how long they can keep an answer. If the answer is cached, DNS can respond extremely quickly. If it isn't, the resolver may need to go searching again. But here's something most beginners never realize. YouTube.com doesn't just have one kind of DNS record. An A record maps a hostname to an IP4 address. And for IPv6, there's the AAA record. A CNAME can create an alias from one hostname to another hostname. And MX records tell mail systems which servers handle email for a domain. And that's only a few examples. DNS can store many different types of information, not just website addresses. So when your computer asks DNS a question, how does it actually communicate with the DNS server? Traditional DNS uses port 53. DNS commonly uses UDP for normal queries, while TCP is also used in situations where it's required. UDP keeps ordinary DNS exchanges lightweight and fast. But DNS isn't limited to UDP. Modern systems can also use encrypted DNS technologies, such as DNS over HTTPS, or DOH. There's also DNS over TLS, or DOT, which protects DNS traffic using TLS. Now let's answer the question that explains why DNS is so important. If DNS resolution fails, applications that depend on host names may struggle to find their destinations, even though the underlying internet may still be working. And here's where this stops being theory. You can test DNS yourself. The result can show which DNS server answered your query and what address it returned. Phrase turned. On Linux and many network engineering systems, you'll also see engineers use a powerful command called dig. Dig gives you much more detail about the DNS response, including the record type and TTL. But there's one more DNS concept you need to understand if you want to troubleshoot networks professionally. Don't confuse the Recursive Resolver with the authoritative server. The Recursive finds answers on your behalf. The authoritative server is responsible for the authoritative DNS data for the domain. So our journey was your device, the recursive resolver, root, TLD, authoritative DNS, and then the answer comes back. And the reason you don't feel all of that happening every time you visit a website is caching. So now you know how DNS finds the address. But there's still one giant question. Once your computer has that IP address, how does it actually get there? That's where routers, TCP, HTTPS, ports, and the rest of networking come together. DNS has done its job. We started with a name, and now we finally have an IP address. But remember, DNS didn't actually connect you to the website. It only helped you find where the website is. So now your computer knows where to go. But how does it actually establish communication with that server? This is where ports come in. An IP address identifies the host, while a port helps identify the service you're trying to reach. For a normal secure website, your browser commonly connects using HTTPS over TCP port 443. With traditional TCP-based HTTPS, the connection begins with a three-way handshake: SYN, SYN-ACK, and ACK. Now the connection is established, and encrypted application data can start flowing. Think about what just happened. You typed a name, DNS found the address, and networking took that information the rest of the way. But what if DNS gives you the wrong answer? DNS problems can make perfectly healthy network infrastructure feel completely broken to the user. So a network engineer separates the problems. Can I reach an IP? And separately, can DNS resolve the hostname? You can have working IP connectivity and still have a DNS problem. One of the first things to check is which DNS resolver your device is actually using. Companies may use internal DNS for private names. Devices can also use public recursive resolvers. These are used for internet domains. You may have heard of public resolvers such as Google's 888.8, Cloudflare's 1.1, or Quad9's 9.99.9. And DNS isn't just for websites. Email, cloud services, APIs, applications, and internal systems can all depend on DNS. That's why the phone book analogy works. Remember, DNS isn't one giant database sitting somewhere. DNS is a distributed, hierarchical system made of many different servers working together. Let's put everything together one final time. You type a domain name. Your device checks its caches. If necessary, the recursive resolver goes looking for the answer. The resolver follows the hierarchy: root, TLD, authoritative server, until it gets the information it needs. The answer comes back with information such as the address and its caching lifetime. Then DNS steps aside, and your browser uses the resolved address to establish the actual application connection. So DNS isn't the internet, it isn't the router, and it isn't the website. It's the system that helps turn human-friendly names into information networks can actually use. Quick test. Which one translates domain names into IP addresses? Router, switch, or DNS? Comment your answer. If you said DNS, you're right. And now you actually understand why. Today you learned what DNS is, how resolution works, caching and TTL, major DNS record types, recursive versus authoritative DNS, troubleshooting tools, and how DNS fits into the bigger networking picture. We started with routers, then switches, and now you understand DNS. But there's one problem. Your computer needs an IP address before it can communicate properly on the network. So who gives it one? DHCP. DNS may be invisible, but every time you type a website name, it's working behind the scenes. It helps you find your destination. Now you understand DNS. If this finally made DNS make sense, hit like, subscribe to the Tech Girl, and comment DNS so I know you made it to the end. And in the next lesson, we're answering the question every device on a network needs to know. Who gives me my IP address? I'll see you in DHCP.